Hello everyone, welcome to AP Physics 1 Unit 3 Ultimate Guide. In this video we're going to discuss everything that you need to know about Unit 3, covering work, energy, and power. Here are the 5 units. The timestamps will be in the description, so feel free to jump around as you need, and hopefully this helps. So what is kinetic energy? So the kinetic energy is basically the energy associated with how much an object is moving. So if we have an object and it has some velocity, it's going to possess some kinetic energy, and we call this translational kinetic energy, as it's moving in like a straight line. So that's where this velocity comes in. So it's also important to note that the energy is a scalar quantity, so it does not have a direction. And we can figure out what the units are. So if we plug in, so if we have our kilograms for our mass and our velocity is meters per second and we square this, the units for energy are kilograms meters squared per second squared. But you won't hear people saying I have this amount of kilograms meters squared per second squared, so we define this as a joule. And so a joule is a unit of energy that you'll commonly see. Alright, so let's do an example. So we have a 7 kilogram ball is thrown downwards 5 meters per second and has a velocity of 10 meters per second when it reaches the ground. What is initial, final, and change in kinetic energy? So let's list out what we have here. So we have the mass of the ball, which is 7 kilograms. We have the velocity initial, which is 5 meters per second. And this is downwards, but you'll see this negative sign won't matter when you plug it into the equation. And the final velocity is 10 meters per second, which is also downwards because the ball is falling downwards. So if we want to find our initial kinetic energy, we know it's 1/2 mv squared. And if we just plug in our values here, we have the mass of 7, this initial velocity, which is -5, but since we're squaring it, this negative will cancel itself out, and so we'll get 87.5 joules. And so our final kinetic energy is going to be plugging in our mass, which is not changing, and the velocity final, which is a -10 squared. So if we plug that in, we get 350 joules. And so now to find the change in kinetic energy, we can simply do the K final minus the kinetic energy initial, which is 350 minus 87.5, which equals 262.5 joules. So something to note is that the kinetic energy itself will never be negative, but the change in kinetic energy could be negative. So we'll learn in the next video about work, and then later how this change in kinetic energy relates to the work. So this is what we have for our work equation here. The work, which we define as W, equals the parallel force to distance, which also equals the force distance times cosine of theta. So what does that actually mean? If, let's say, we have a box and a force is being applied to it at this angle, and let's say the block travels this distance. The work is basically how much force is applied over this distance, and that's what defines the work. So this parallel part of the force would be this. It's the parallel force to the distance, which also, if we want to find this component of force, equals cosine of the angle that the force makes with the distance. So that's how we're getting this equation. So something to note is the units of this is going to be a Newton times meters, which equals a kilogram meters per second squared times a meter, which if we multiply these meters together, we'll end up getting kilograms meters squared per second squared, which equals a joule. So it's also a unit of energy, just like kinetic energy would be. So this is also going to be a scalar quantity, but work can be either positive or negative, and we'll show a few scenarios down here. So let's say we have a box that is applied a force like this and travels a distance like this. In this case, the work is going to be positive because force and distance are in the same direction. But if we have a different box and the force is being applied in this direction but the distance is this direction, in this case the work is going to be negative, because if we did FD cosine of theta, this theta would equal 180 degrees, and so cosine of theta would be equal to -1, and so you would have a negative work. And now let's say we have a box that's being pulled with a force upwards, and it travels this distance. Well, in this case, the work due to this force is going to be equal to 0, because the force is not applying any force in the direction of motion. So in this case, the work will be 0. And so one last thing to discuss, if you get a graph of, let's just do it up here. If you have a graph of force times the distance, let's say it just looks something like this, right? If you wanted to find the work, we know the work equals the force times the distance. So as long as this force is the parallel force to distance, the area under the curve will be equal to the work done over this certain distance. So if you're ever given a graph, you can find the work graphically by finding the area. Alright, so let's do a couple examples relating to work here. So we have Bob picks up an 8 kilogram box, a distance of 1.5 meters, and brings it to his house that's 5 meters at a constant speed horizontally. He then places the box back down 0.5 meters. How much work does Bob do on the box over this entire situation? So let's write out what we have. So we know the mass of the box is 8 kilograms. So we know the first distance is picking up the box 1.5 meters. He then travels a second distance of 10 meters and then places the box back down 0.5 meters. So we need to figure out what the total work over the situation is. But you'll notice that we can't just add up these distances and say that the force is going to apply on these equally, because different things are happening. So let's draw what's actually happening. So first, we have the box, and it's being picked up with a force, applying this force upwards. And it's traveling this distance, or we'll just call it d1. So that's the first situation. And so now the box is up here. And so now Bob is walking with this box this direction, a distance of d2. But the force that he's applying is still going to be just holding the box upwards, that normal force. There's no force actually pushing this box this way. So the force is only up and down as the box is moving at a constant speed of force gravity and the applied or normal force that's holding this box up. And then we have placing the box back down. So now the box is over here and it's going down 0.5 meters. But we're trying to find how much work does Bob do on the box. So the force gravity is pulling this box down, but Bob is still applying this force upwards. So the force is up, but the distance is down. This is equals d3. So if we want to, let's do it for each situation. So we have work from the first distance is going to be the force that Bob is applying times the distance, and we know these are in the same direction. So if we have cosine of theta, theta is 0, so this cosine will just be 1. But what is this force going to be? So if we draw our little free body diagram for this first situation, we have the force due to gravity of the box and the force applied from Bob that lifts this box upwards. But they're going to be equal because he's lifting the box up. Right, and we can assume he's lifting it up at like a constant average speed so that these forces will be equal. So this force applied here is just going to equal the force due to gravity. So we know this will equal the force due to gravity times distance, and the force due to gravity is just simply the mass times gravity times distance. And so that'll be the work that he does during the first time. So we can plug in the variables because we have all these variables. As the mass is 8, gravity is 9.8, and the distance he travels is 1.5. So this is 117.6 joules. And so now let's talk about situation 2. So in this case, we have this angle equal to 90 degrees between the force and the distance. And cosine of 90 degrees is just equal to 0. So the work along this path is just going to be equal to 0 because Bob is not applying a force. He's just walking with the box, and the force is actually happening like as he's like speeding up and slowing down under his feet. So he's not actually applying any work to the box as he walks with it. Okay, and then for the third situation, now when Bob is holding this box, you may think the force is in the same direction, but what's actually bringing the box down is the force due to gravity. He's holding the box from falling. He's bringing that box downward, so the force is actually in the opposite direction, and the work on the box is going to be negative because that cosine theta will be -1. So if we have this force applied times distance cosine of theta, this cosine of theta is going to equal cosine of 180 degrees, which equals -1. So this will equal a negative force applied times distance. And in this case, the force applied will equal the force due to gravity. So we'll have a negative mg for this situation as well. And we can plug in the values. So the mass is 8, then we have 9.8, and then a distance of 0.5. So if we plug that into a calculator, we'll get negative 39.2. And so now we want to find the total work. So we can just simply add up all the works. And so we can plug in what we got. So we got 117. The first one, we know the second work was 0, and we can subtract that last work. And so the final work will be 78.4. And so you can notice that it only depends on this initial and final position of the box relative to the vertical, because he's only doing forces applied in the vertical direction. Alright, let's do one last example here. So we have Bob pulls a 15 kilogram box up a rough incline with an angle of 20 degrees from the horizontal. He applies a force of 300 newtons parallel to the incline and travels 9 meters. The coefficient of friction is 0.37. We want to find what is the work done by friction and what is the work done by gravity. So let's write out what we have first. So we know the mass of the block is 15 kilograms. The angle that the incline makes is 20 degrees. The force applied is 300 newtons. We know the coefficient of friction, and since it's a sliding box, we know it'll be kinetic friction, is 0.37. And the distance he travels is 9 meters. So if we draw our incline here, it'll have an angle of 20 degrees, and the box is going to be like this, and it's going to be pulled up this incline here. That'll be the force applied. Okay, so let's first draw out kind of the free body diagram on this box here. So there'll still be a force due to gravity coming down, a force normal coming off of it, and then we know there's gravity because it says we know there's friction because it says there's a coefficient of friction. So the friction will be always in this opposite direction of motion. And so we know that this box travels a distance of d, and that's 9 meters. So we want to know what is the work done by friction. So we know what work equals. So the work equals the force times the distance cosine of theta. So in this case, we need to figure out what do we need for the work of friction. So we know it'll be the force due to friction that's causing the work. The distance will be the same because it's how much the box is moving. Cosine of this theta, I'm going to call theta f. It's the theta that is related to the friction, force, and motion. So since friction is in this opposite direction of the distance, because we know the distance will be that way, as it's pulled up the incline, this cosine of theta will go to -1 because it's 180 degrees. And when you're working with friction, it's always going to be 180 degrees from where motion is. So we can simplify this to the work equals the force due to friction times the distance. Now all we need now is the force due to friction, but we're not given that, so we're going to have to use our force equations. So we know what force friction equals in terms of other variables as the coefficient of friction times the normal force times distance. So now we just need the normal force. So we can use our y equations here. So if we look in the y direction, and we can set our y direction to be at this angle here, so that we'll have our force normal equals this Fg in the y direction. And so if we want to solve what out this is, we're going to have this angle here, which equals theta, is also going to equal to 20. So we're going to have this cosine define this y. And so we have Fg times cosine theta because of where the angle is off the horizontal. And then we know Fg is equal to mg cosine of theta. And so now we know what Fn is, and we have all these other variables, so we can plug this back into the work by friction. And so now we have everything to solve the equation, so we can just plug in the variables we're given. So 0.37, the mass is 15, gravity is 9.8, cosine of 20, and the distance is 9 meters. So after we plug all that in, we'll get the work by friction is a negative 460 joules. And so friction work will pretty much always be negative because it's slowing down, or it's in the opposite direction that the box is trying to move. So the box is trying to move that distance, but the friction is doing work against the box moving. So now we need to know what is the work done by Earth's gravity. So I'm going to scroll down a little bit here. But if we want the work due to gravity, then we're just going to use Fg is going to be what's causing the force times d cosine of this theta, and I'll just say theta g, right? So we could try to find the angle that's between the force due to gravity and the force applied, which wouldn't be too difficult. We could add 20 to 90, but we could also use the version of the work equation where the force is parallel to the distance. And we know the force that's going to be parallel to the distance is going to be that Fg in the x direction. So then we can plug in our work due to gravity as Fgx times d. But we know that since Fgx is in this opposite direction of the motion, it'll be a negative Fgx times d. And so now we can find what Fgx is, which is just the mass times gravity, because that's force due to gravity. But then the angle from this incline is cosine, or it's going to be sine because it's off the parallel. So it'll be sine of theta, and then times the distance. And so now this theta is still this 20 from up here, and we didn't have to find any weird angles, and now we can plug in all the values that were given. Sine of 20 times the distance of 9. And so the work due to gravity is going to be a negative 452.5 joules. And so since this box was sliding up the hill, the work is doing negative work. But if the box is sliding down the hill, the gravity would be doing positive work. So that's where this sign comes in. So really the main thing to know here for work is that we know the work equation, we just have to find what force is doing the work and then solve for that force using force balance equations that we learned about in Unit 2 of Physics. So the work energy theorem. So this is the main idea. The work equals the change in kinetic energy, or really the change in energy in some cases. So if we write out what the work equals, we know the work equals the force times the distance cosine of theta equals the 1/2 mass times the velocity squared. And since we're looking at the change in kinetic energy, it'll be the velocity final squared minus the velocity initial squared. So make sure you square these before you minus. You cannot put the square on the outside. And one other thing you might see when you're solving problems is you might see some graph that looks like where we can show this change using like a bar graph. So let's say there's some initial kinetic energy and then some work is applied. Well, this final kinetic energy would have to be this amount plus this amount. So the final kinetic energy would be higher if you add work. But if you were to subtract work, it would be less. So we'll see that when we do some examples. Alright, so let's do a first example here. So we have a box, or a bob pushes a box and then releases it, allowing it to slide on a surface with a coefficient of friction of 0.3 between the box and the surface. The box slides 5 meters before coming to rest. What is the initial speed of the box? Okay, so let's write what we have first. So the distance we know the distance travels 5 meters. We know the coefficient of friction is going to be kinetic because it's sliding, equals 0.3. And we're looking for the initial speed, v naught. So if we try to understand what's happening, a box is pushed with some force and then is released. So then it's released and it slides like this until it eventually comes to rest. So it travels some distance and then stops. So there is some v initial, and then v final equals 0. Alright, and friction is doing a force in the opposite direction because it's slowing down this box. That's the force that's doing the work that is slowing down the box. So if we fill in our chart over here, we know there's some initial kinetic energy because the box has some initial velocity. And we know the final kinetic energy is going to be 0 because the velocity final equals 0. So this will be at 0. And so the work that's done has to be the negative of that initial kinetic energy. So that's what our graph over here would look like. So let's start with our main equation. So we know that the work equals the change in kinetic energy. That's the big idea. So we can plug in what we know for work. So we're looking for the work due to friction because that's what's slowing the box down. That's what's causing that change in kinetic energy, times the distance, cosine of theta. And we know friction work is pretty much always going to be, well, it's always in the direction opposite to motion. So this is going to be go to -1 because theta is 180 degrees. And then we know our change in kinetic energy is the velocity final squared minus the velocity initial squared. But we know this velocity final squared goes to 0. So if we simplify this, we get the force of friction times the distance, and this is negative, equals, this should not be a negative actually. This should start as positive, but since this velocity initial is negative, we can bring the negative out. And we get this, so then the negatives cancel, and we'll get force due to friction times distance equals 1/2 mv naught squared. So now we need to solve for this initial velocity. So we don't know the mass, so we need to figure out how we're going to get rid of this mass. But we do know the distance, but we don't know the force due to friction. So let's draw our free body diagram, because I think that'll help us out. So we know that there's going to be some force due to gravity of the box, some force normal, and then the only other force acting on the box while it's sliding is this frictional force. So that's the only other force that's going to be applied here. And we know that the force of friction is equal to the force normal times the coefficient of friction. And because this force normal equals force gravity, because it's not accelerating in that direction, so we'll have the coefficient of friction times force due to gravity, and we know that the force due to gravity is just equal to mass times gravity. So if we plug that back into our equation over here, we get the coefficient of friction times mass times gravity times distance equals 1/2 mv naught squared. And now we get these masses that cancel, and so we have the coefficient of friction, gravity, distance equals 1/2 v naught squared. So now we can solve for v naught squared by saying 2 coefficient of friction gd, and then take the square root of both sides, and get this as our final equation. And so now we have all these variables, so we can go ahead and plug these in. Okay, so if we plug these in, we get a velocity initial of 5.4 meters per second, and that'll be our final answer. So that's how we can relate the kinetic energy to the work to solve for some variable component. Okay, so let's do one more example. So we have a car accelerates from rest at 5 meters per second squared. How far has the car traveled when it reaches a speed of 8 meters per second squared? Okay, so we know the acceleration, first off, is 5 meters per second squared. And so it says it accelerates from rest, so that means we know the velocity initial is 0, and we want to find the distance at a speed of 8 meters per second. And so we want to know how far the car has traveled, so that'll be the distance. So that's what we're trying to find. So let's fill in our graph over here. So in this case, we know the velocity initial is 0, so there's going to be no kinetic energy to start. But then it reaches some kinetic energy when it has the velocity of 8 meters per second. So that means this work is going to be equal to the final kinetic energy. And so we can start with the original equation, saying work equals change in kinetic energy. But when we write it out, we'll have the force times distance cosine of theta equals the 1/2 m vf squared minus v naught squared. But this v naught goes to 0, so this component right here is just the final kinetic energy. So we could use this graph just to immediately go to work equals k final. So now we need to decide what is the force that's actually doing the work. So we're just looking at these initial and final positions. So we just know some force, some net force is acting on this car to allow it to accelerate. So we can actually just put F net here, because we're looking at the net force in the x direction, because we know it's accelerating in the x direction, times the distance. And this cosine is just going to go to 1, because we know the force is in the same direction since it's accelerating. And the speed is increasing. So then we still have this part. Okay, so now what is F net equal? Well, we know by Newton's second law, the force net is just the mass of the system times the acceleration of the system. And so now these masses cancel, and we want to know this distance, so we can divide by acceleration. And we can get this equation here. And now we have all these variables. We can just plug these in and get a distance of 6.4 meters. And so you might be thinking this equation might look a little bit familiar, and that's because you can also solve this using normal kinematic equations, since there we have a constant acceleration. And so if you were to do this using kinematic equations, you could use this kinematic equation where the velocity initial is still 0, and you get vf squared equals 2a, and then in this case the change in x is the distance. And so if you want to solve for distance, you would get the same equation as we had before by using kinematics. So this is how, that's the cool thing about physics though, is that as long as you're not breaking any principles, you can use different methods to get the same answer. But this won't always work, because in this case we had this constant acceleration, and sometimes doing energy is going to be a lot easier than kinematics. Sometimes kinematics will be easier. So it's important to realize when you can use different techniques, but a lot of times it's going to be easier to use energy actually than kinematics, but in this case it shows that you can use both. So the gravitational potential energy is equal to the mass times gravity times the height. So let's say we have a little situation over here where we have like the ground, or let's draw this lower. Let's say we have the ground right here, and if a ball was right here on the ground and we took this to be height equals 0, then this would have a 0 potential energy. But if the ball was up here, now it has some height, and so there would be some potential energy here. And if we had a ball below the ground, then it would have a negative potential energy. So this would be a positive potential energy. And so the thing with energy is it all depends on what you call your reference state. So if we said a new reference was right here and we called this reference height equals 0, or our potential energy here would now be 0, and these would both be negative potential energies. So depending on where you call your reference, it will change the value. So it's important that you pick a reference that makes the question the most easy, and we'll talk about that later. And so a note on the units for potential energy, we have kilograms, and then gravity is meters per second squared times the height, which is meters. So this is kilograms meters squared per second squared, which equals a joule. So this is indeed a unit of energy, just like kinetic energy or work. And so some other potential energies you might see is like a spring potential energy, which equals this equation, or you might see like gravitational, as in planetary potential energy, which can be described as this formula. So we'll talk about these in later units of physics. This will be talked about in Unit 7, and this will be talked about in Unit 6. So we won't discuss these right now, but these will be different potential energies you might see, and we'll cover those later. Alright, so let's do an example for gravitational potential energy here. So we have Bob, who is 68 kilograms, rides a water slide as shown below. So he starts at point 1, up here at 50 meters. He travels down, back up, and then all the way down. So we just want to figure out what is his potential energy along this path. So we want to know, in this first part, what is Bob's potential energy at point 1 relative to point 4? So when it says relative to point 4, we're going to make point 4 the reference point where the potential energy equals 0. So that means we can base our height off this reference point at point 4. So we know that our height now is just going to be this 50 meters, because this 50 meters is from this bottom reference point. So we know our U potential energy is just mass times gravity times height. So the mass is 68. That was not a 6 or an 8. The mass was 68 times gravity, which is 9.8. And so the height, we would use 50 meters. So if we plug those in, we'd get a potential energy of 33,320 joules. Okay, so what is Bob's potential energy at point 1 relative to point 2? So now, the mass and gravity aren't going to change for any of these, because he's not changing his mass, and the gravity is always constant. But now we have point 1 relative to point 2. Now note that he's still going to have the same, he's still, in the same position, but this time we're calling this the reference point, which means that we need to find this height, and we'll call this height B for question B. So height B is going to be equal to this total height minus the height of this at point 2. So it'll be 50 minus 25, and that'll give us 25 meters, because he's 25 meters above the reference point. So now we can use the same equation we just used and say the mass times gravity times this height from the reference point, which is 25 meters, equals 16660. Okay. So that shows that even though they're in the same position, he can have different potential energies because the reference is different. And so let's do another one. So he's at point 2 now, but we want to know the potential energy at point 2 relative to point 3. So now we're making point 3 the reference. So we need to know this height to get from point 2 to point 3, right? So if we want height, say C, then we can do the final, the initial height that they're at minus the reference height. So it'll be 25 meters minus the 35 meters, which is a negative 10 meters, because he's 10 meters below the reference point. And so when we go to plug in our equation here, we'll still have mass times gravity. And now for the height, we're going to plug in a negative 10 meters. And so this potential energy is actually going to be a negative potential energy. And basically all this negative means is it's below whatever we call the reference. And so we'll see, why is it that we can just call the reference anything, and how is that not going to mess up all the further calculations? So let's see this in part D. So we have, what is Bob's change in potential energy as he travels from point 1 to point 2? So in this case, it doesn't tell us what reference to use. It just says we want the change in energy. So we can find this potential energy at point 1 and 2 using any reference, as long as we use the same reference when we calculate both of them. So in this case, it makes the most sense to use point 4 as the reference, because it's at 0 meters off the ground. So it'll make all the calculations much simpler, and we can just use these values that we're given, right? So if we want to find the change in potential energy from point 1 to point 2, if we want to find the change in gravitational energy, we can simply find the gravitation at the final point, point 2, minus the gravitational potential energy at the initial point. And so this will equal the mass times gravity, the height initial minus the height final. So if we go ahead and plug this in, we would have the 68 times 9.8. And so the height initial, or it should be actually, sorry, it should be height final minus height initial, because it's potential energy final. Yeah. Okay. So we have the final height minus the initial height. So the final height here is going to be 0.2, because that's his final height he gets to, is 25, and he starts at a higher point of 50. And so if we were to plug this in, we would get a negative 16660 joules. So that's the change in potential energy. So even if we were to choose, let's for example just choose 0.2 as the reference, right? If we choose 0.2 as the reference, we want to use this height B again. So we already know Bob's potential energy at point 1 relative to point 2, which is this energy right here. And so now, if we want to do the change in potential energy using point 2, we know the final is going to be 0 because we set this reference to at point 2. So if the reference is at one of the points, we can automatically set that to 0, and we minus the initial, which is initial from the reference point. And since we already did 1 relative to 2, we're just going to subtract that 1660 joules, and notice we get the same answer as we got when we chose the initial point as the ground. So changing the reference point will only change each individual potential energy, but the change in energy is going to be the same. So now let's do this last problem here. So how much work does gravity do on Bob as he travels from point 1 to point 2? So if we wanted to solve this how we know how work, like using our normal work equation, equals force times distance, we can do this because the force that's acting on Bob by gravity is just Fg times the distance. And notice Fg equals mg, so we just get this mg times distance, which in this case is the height from point 1 to point 2. And so the work just equals the mg times the height, which we know it's still going to be 68, 9.8, and the height from point 1 to point 2, as we found earlier, was 25. So we will get 1660 joules. And notice this work equals the negative change in this gravitational potential energy, because we had a negative here, so the work was the negative change. And what will be easier to think about in most cases is that the change in gravitational potential energy is the amount of work that's lost in the system. So that's the big idea. The one other thing about potential energy here that I should have mentioned is that when we're doing potential energy, we have to define our system with two separate objects. So our system here was, let's use this highlighter, was Bob, but then Bob also has to be relative to something else. And in this case, Bob is relative to the Earth. So the Earth is the other part of the system. So it's a Bob-Earth system. So if there's anything else in the system, it can't have potential energy. So if you here define the system as like the object in the Earth, It's basically saying that they both need to be included so that you can relate the energies of the two. So a conservative force is when work only depends on the initial and final position. So an example of this would be like the force due to gravity. It only depends on the initial and final position when we're relating the energies. So like gravitational potential energy, for example. A non-conservative force is when work depends on the path that's traveled. So an example of this would be the force due to friction, or a force of like air resistance. We'll say like a resistive force. So for example, like if we have, let's say we have an object like this, and we have this Earth object system. This force due to gravity only depends on the final initial positions when we're relating the potential energies. So this force is conserved within this system. But if we have friction, if something travels from here to here, the force due to friction is going to be less than if you travel in some long path to get from here to here. At every point there's more and more friction. So the way we can think about the non-conservative forces is that it's losing energy. There's some energy leaving the system by this non-conservative force. And so the big equation that we can define here is that this work done by non-conservative forces equal the change in kinetic energy plus the change in potential energy. So if there's no non-conservative forces, then this will just equal 0. But if there is some non-conservative forces, it'll equal the work due to the non-conservative forces. So this is one big equation here. And so you can think of this work due to the non-conservative forces as energy entering or leaving the system. So let's see how that works in an example. Alright, so we have Bob is 70 kilograms and rides a water slide as shown below. He starts at a height of 50 meters, slides down and reaches a height of 38 meters before coming to rest and sliding back down. If he traveled a total distance of 120 meters, what is the average frictional force on Bob? So in this case, this is his initial height here, which is 50 meters, and he reaches this height of 38 meters when he comes back up, and then he slides back down. So let's list what we have here. So we have the mass, which is 70 kilograms. We have his initial height, which is 50 meters. And so we know what is his initial velocity, right? So you say like he starts sliding down, but we can say that this initial velocity is 0 because he starts and then gravity starts to take him down this hill, right? So he starts from rest. And so that's the initial conditions, and so his final height he reaches is this 38 meters, which notice is less than his initial height. And his velocity final is also going to be 0 because it hits a point of rest before it starts coming back down. And then we know the total distance that he traveled is 120 meters. We want to know the frictional force. Okay, so let's start by drawing our graph of energies. So now we're going to have a kinetic energy initial potential energy, the work from non-conservative forces, and then these final energies. So at the initial point and the final point, these velocities are 0, which means there's going to be no kinetic energy for the initial or the final. But the potential energy starts at some high point of 50 meters and then reaches a final potential energy that's slightly lower but still above the reference point, which we will call the ground to make this easier. So we want to know the work, which must be some negative work that's taking energy away from the system. In this case, that's going to be the friction. So if we start with our work energy equation, we get that the non-conservative forces equal the change of the energies. So we know this kinetic energy is just going to be 0 because the change is 0 because they both are at 0 at the initial and final. But we want to relate these two. So we know the work, non-conservative work, is from friction. And we know this change in gravitational potential energy will just be mass times gravity times the change in height. So we have the change in height. So let's break up this work due to friction. So that'll be the force due to friction times the distance times cosine of theta equals mg, and I'll write this as hf minus h initial. And so this cosine theta is going to just going to go to 1, because at every single point that he's traveling, the force of friction is perpendicular to the motion he's traveling in the opposite direction, so this will actually be -1. And so now we can pretty much rearrange this equation and solve for the force that the average frictional force here. So if we set this and divide by the distance, we can get the frictional force. And so now we can just plug in the numbers that were given and solve for the frictional force. So these are the change in heights over the distance, which is 120. And so this frictional force that was applied on average is 68.6 newtons. Alright, so let's go over when we can apply conservation of energy. So the main idea here is that the mechanical energy equals the kinetic energy plus the gravitational potential energy. That's the total energy. So if the work from non-conservative forces equals 0, then the change in mechanical energy will also equal 0. And so that means, using the equation from before, we'll have 0 equals the change in the kinetic plus the change of gravitational, and we'll get this kinetic energy initial plus the initial potential energy equals the final kinetic energy plus the final gravitational potential energy. And so when we have this situation, we can call this a closed system. And that means all the energy will be conserved and no non-conservative work is done. And you should note that energy is always conserved overall, but sometimes it'll leave the system as the form of like heat energy or thermal energy. It could also leave as like chemical energy or electrical or sound. So a lot of ways you can lose energy, but if energy is conserved in the closed system, then we won't have any loss of energy outside the system, and it will only be transferred between kinetic and potential. So let's see how that works with a final example here. So we have Bob jumps off a trampoline into a foam pit. He leaves the trampoline at a velocity of 5 meters per second up and lands with a velocity of 7 meters per second. How far did he fall below the trampoline, assuming the air resistance is negligible? Okay. So we're given the initial and final velocities. And note that since we're dealing with scalars and energy, we don't really care the direction that he's falling versus jumping. That's the nice thing about energy versus kinematics. In kinematics, you have to be really careful about your directions, but with energy, since we're dealing with all scalars, it doesn't really matter. It's just how the speed that he's traveling for the energy. So we want to know what was this height that he fell, because he's on the trampoline, right? He's jumping on there, and he jumps up and then falls down a certain height, and that's the height that we want to find. Alright, so if we write out our energy graphs for a conserved system, we only care about these initial and finals. So we could put the non-conservative work here, but we know it's going to be 0 because we've defined this as a closed system, making the system Bob and the Earth. So he's going to have some initial, I'll do this in a different color, he'll have some initial kinetic energy. He'll also have some initial potential energy. And then we know he'll have some final kinetic energy because he lands with 7 meters per second. But if we define the ground or the foam pit as the potential energy equaling 0, that's the reference point, then there'll be 0 potential energy at the end. And so all of this initial potential energy is converted to kinetic energy, and that's how we can find the height. So let's start with our equation. We have the kinetic energy initial plus the gravitational initial equals the kinetic energy final plus the gravitational final. I should say final. So we know this is going to be 0 because we just defined this as the reference. So now we can turn all of these into their equations. So we have 1/2 mass velocity initial squared plus mg. In this case, we'll say h because that's the height that we want to find, and the final, which is 1/2 mvf squared. So now we have all these variables, but we don't have the mass. But notice that mass in this case just cancels out. And so I'm also going to multiply by 2 to the whole equation to get rid of all the fractions. So we just have v naught squared plus 2gh equals vf squared. And so now we can move our equation around to solve for h. Should be minus here. And so we can rearrange for h equaling to vf squared minus v naught squared over 2 times the gravity. And so if we plug in the variables that we were given, we would get a height of 1.22 meters, and so that's how far he would fall. Alright, so the main thing about the energy is if we can define it as conserved, there's no work done outside of this system, so all the energy is just going to be transferred around between kinetic and potential, and that's the main idea, and that's how you can use that to solve a lot of problems. And notice we could solve this with kinetics, or not kinetics, kinematic equations, and we could use our initial and final and use an equation and have gravity, and that's all fine, but usually energy is a little bit easier because you're only dealing with scalars and it only depends on the initial and final positions, which is really nice. So the power is defined as the work over the time or the change in energy over time, since change in energy equals work. So the unit for this power is we have an energy unit, which is a joule, over time. So we can say seconds. And so this joule over seconds we call a watt, or a big W, so that's a watt. So you may have heard like kilowatt or something. So that's what a unit of power is. And another way we can define power is, since we know power equals work over time, and work equals force times the distance, cosine of theta, over time, we have this distance over time piece right here. And we know that distance over time just equals the velocity. So we can rewrite power as equal to the force times the velocity, cosine of theta. And so you may have questions that give you velocity, and you can use that to solve for the power. Alright, so let's do an example with power. So a crane lifts a 500 kilogram block of metal 10 meters above the ground. The crane applies a constant power of 750 watts. How long does it take for it to lift the block? Okay, so let's list what we know. So the mass is equal to 500 kilograms. The distance the block travels is 10 meters. And the power is 750 watts. Okay, so we know the power equals the work over time. And we know the work is just force times distance cosine of theta over time. So now we just have to decide what's actually doing this force that's causing the work. Well, we know the crane is lifting the block. So if we were to draw a quick free body diagram, this force applied, or the force by the crane, is what we care about. That's what's causing the power. So this is going to be the applied force. And since the block, let's say we have our block here, is moving in this direction, the force and distance are in the same direction and they're parallel, so this cosine of theta will just go to 1, since theta is 0. So we can rewrite our equation as power equals the force times the distance over time. And so now we're just looking for time, so we can rearrange the equation for time as the force applied times distance over power. But we're not given the force applied. But we can see from our free body diagram that the force applied is equal to the force due to gravity. So we can say force applied equals force due to gravity, and we know force due to gravity is just mass times gravity, and we have the mass and we know gravity because it's constant. So now we have all the variables needed because we can plug mg into here using this equation, times distance over power. And so now we have all these variables. So we have the mass, we have gravity, we have the distance, and we have the power. Okay, and if we plug this into a calculator, we get that the time it took was 65.33 seconds, and that'll be our final answer. Alright, that was all of Unit 3. Feel free to go back and rewatch any parts as you need, and stay tuned for Unit 4 where we start talking about linear momentum. Alright, thanks for watching.